Hello, and welcome to Solving Electromagnetic Challenges, an EMA webinar series. My name is Matt Colding, and I'll be your host for today's presentation on the introduction of Ansys STK Shield Plus. To submit any questions that you have during today's webinar, please use the Teams webinar Q&A feature located at the top center of the Teams menu bar. After the presentation, we will address any submitted questions. Should there be any unanswered questions, by the end of the webinar today, we will address them over email. Our speaker today is Kevin Miranda. Kevin Miranda is a principal scientist at EMA and the lead product manager of Ansys EMC Plus, Ansys Charge Plus, and Ansys STK Shield Plus. Kevin's expertise is in atmospheric electricity physics, elementary particle physics, and computational physics. Throughout webinars or at conferences, Kevin gives regular updates on the development progress of EMA's software solutions. He's very excited to discuss this landmark addition to EMA's software suite. Without further delay, I give you Kevin.
Thanks, Matt. Yes, I'm so excited to be able to talk about a new product that we've developed here at EMA in partnership with STK, Ansys STK Shield Plus. We're trying to bring a synergy between the two solutions, as there's a lot of ways we can help each other in terms of a solution at STK and a solution and the tools that we have in EMC Plus and Charge Plus. So this is what we were able to provide to the community, Ansys STK Shield Plus. Just a quick summary and introduction of EMA, electromagnetic applications. We have about 60 plus employees, almost 70. Our headquarters are in Denver, Colorado, and we have a couple offices across the East Coast as well. We work on several active SBIRs and STTRs, and we work regularly with the Navy, Air Force, NASA, and Space Force. Our expertise is in consulting, in simulation, and in measurements as well. We work with companies around the world, and we like to have this synergy between the three to be able to help each of the pillars that you see here. And so having software is good, but making sure that it's validated with measurements is even better. And at EMA, we can do those measurements. Our expertise in EMI, EMC, in EMP, RF interference, antenna performance, spacecraft charging, lightning, HERF, complex simulation measurement combinations, and then most recently some multi-physics aspects of plasma modeling that we can also handle. We do consulting across many different industries. We are experts in our fields, and we're able to help aerospace, military, automotive, rail, energy, and consumer electronics solve EMC problems and help out to get to your solution as quick as possible. We also specialize in first-of-a-kind scenario. We will work to solve problems that have never been encountered before on the electromagnetic realm. We have tools that we use to be able to do that, like our software tools like EMC Plus and Charge Plus, and we will train you on how to solve these problems with the tools. And we want to make sure that you also become proficient in our softwares through our consulting services. We also do much more long-term consulting scenarios where we will be available for long-term support for your teams to be able to solve some EMC concerns. We have clearance capabilities, cleared employees, and we can really handle any level of problem complexities. This is an example of one of our test facilities that we are able to solve and replicate space plasma environments to be able to understand the risk of charging in ESD in our chambers. We use that to characterize materials, to validate simulation. And so there's a lot here that we can do. And this is in our office in Massachusetts. And we have a very strong team of experts out there as well. EMA is a technology partner of Ansys. Sorry for this very bright white slide. It's a bit of a clash in the flow, but I really want to highlight that we are developing the software here internally, and we distribute our softwares through Ansys. We are very well known Ansys EMC Plus and Ansys Charge Plus, which I'll go into a little bit more detail in a bit, and then now Ansys STK Shield Plus as well. So I want to give you an introduction to radiation and space radiation and also electromagnetic radiation, just for understanding what we're trying to achieve here with STK Shield Plus. So in orbit, or even on the surface of the Earth, there are a lot of sources for radiation, and radiation can come in the form of particles, but also in the form of electromagnetics. And so here we are talking about, in this deck here specifically, for high energy particle radiation that could be coming from the sun, also from particles trapped in the Van Allen belts around the Earth, or even galactic radiation like cosmic rays coming from far away with very high energy and interfering with our electronics in space. And so we want to be able to understand these phenomena so that we can properly shield ourselves from these effects. Solar energetic particles are continuously emitted from the sun. You may have some transient phenomena when you're in the shadow of the Earth, for example, but typically you're going to have to deal with the radiation coming from the sun. We're talking about ions, electrons, and photons with energies greater than 500 MeV that will be problematic to a deep dielectric charging, for which we have to radiation harden against, things like that. And so we have to be able to add additional shielding or find mitigation effects at the electronics level to be able to deal with that radiation. There's also electromagnetic radiation coming from the sun. There's light at a certain spectrum, 5,800 Kelvin. There's intense UV light that comes from the sun that we have to be able to handle. The Earth radiation, there are multiple levels. We have to worry about radiation trapped in the radiation belts. These are particles that maybe were emitted with the sun, but that are trapped in the magnetic fields and accelerated in some way, mainly electrons and protons. There is a risk of charging and ionizing radiation effects on the electronics, on the satellites, that we have to be able to manage, and also health risks as well if we spend too long in transits in those belts or in those regions as well. And then atmospheric particles, here we're talking about upper ionosphere, for example, with lower energy electrons and ions, also oxygen, nitrogen, things that we have to understand that are a little heavier, but that are present, often associated with drag effects on our satellites, but can also lead to charging phenomena that could be problematic. And then some of the radiation that even more energetic, from cosmic rays, galactic cosmic rays, and anomalous cosmic rays that come from even outside the galaxy. These have very, very high energy and will leave charge behind and create an upset in your electronics. They're hard to shield. It's sometimes impossible because it would require too much weight. So being able to handle and understand these phenomena is important as well. The penetration through shielding is very high, very consequential in terms of health as well. And so being able to screen these cosmic rays are important. And then there's local radiation around the satellite. We have to worry about propulsion systems, creating additional plasma environments that can lead to various charging phenomena that we have to understand well. There could be outgassing material as well that will just lag around the spacecraft and that we have to handle. There are surface potential effects. So if you actually shine light on a material, you'll create electrons. Being able to handle that properly is important. And then there's other types of particles that are larger, for example, like debris and things like that. But we're not dealing with that with Shield Plus. And then electromagnetic radiation, that is a big one as well. And there are many sources of electromagnetic radiation. We focused on aircraft and satellites. We'll kind of discuss also aircrafts here in this case. A lot of these can also affect satellites as well. So being able to model these effects on all those platforms is important. And so here for electromagnetic environment effects, you can see things like lightning attachment will have current flow through a structure, but also indirect lightning effects. We have electromagnetic pulses that can be generated from natural causes or not, and that will interact with the aircraft. There's various statics, and there's also antennas that will emit radiation in various profiles with various frequency spectrum that we have to be able to handle and shield ourselves from in some cases as well. And so being able to deal with all these scenarios. We have a lot of standards that are present that define the thresholds that are recommended for each of these scenarios. You can see a subset here in MIL standard 461 for a lot of ways to design to sustain these problems. And so what we've done with Shield Plus is you'll see we have created automatic workflow like a shielding effectiveness workflow to be able to give a quick assessment on if we have to do a further analysis on these problems. So the solution Ansys STK Shield Plus is based on the technology within Ansys Charge Plus, Ansys EMC Plus, and STK. And so I want to give you a quick outline of what Ansys EMC Plus and Ansys Charge Plus are in case you have never seen them. So Ansys EMC Plus is a tool within the discovery interface, which leverages a finite difference time domain solver, full wave electromagnetic solver to be able to model basically the interaction of electromagnetic fields with a complex structure, which is your CAD with material properties, as well as with cables and with various features on the CAD to understand how that field couples to the sensitive equipment on the inside of the geometry. And so we can tackle things like E3 problems, very complex cable models, PCB models for EMI, EMC problems, and RFI setups. And so these are leveraging very advanced physics tools, and these simulations and workflows sometimes are take time to build. But in our case for Shield Plus is we've created more streamlined workflows to be able to solve these problems quickly based on the information that we can get from STK. Ansys Charge Plus is our more multi-physics tool, which also has electromagnetic solvers in it. One of them is a finite element method and time domain, also for full wave electromagnetics, but also much more advanced Monte Carlo particle physics tools. This is also integrated in Ansys Discovery, so you can manipulate CAD and prepare your simulations. And then we can tackle effects such as space environment effects, ESD testing, discharge modeling, and electromagnetic plasmas as well. And so there's a lot inside the tool to be able to tackle multi-physics problem related to electrostatic discharges, plasmas, charging effects, radiation effects. And so we've also created more optimized and streamlined workflows to solve these problems that we have now as part of STK Shield Plus. So a little bit about the technology in EMC Plus. I've highlighted the physics and the numerical solutions that you will find in STK Shield Plus. So in EMC Plus, we start from a very complex 3D CAD geometry where we have detailed information about the materials, about the thickness of the bodies, about so we can capture composite materials, we can capture metallic, and so on. And then we also model the source of the electromagnetics. So if you have a plane wave, for example, or a pulse or a lightning strike, we can inject current and voltages inside the system in ways that we to be able to reproduce physical sources and how they interact with the structure. And then the more detailed aspects of the problem is when we have to handle how that electromagnetics, once it's inside the system, couples to harnesses or cables that will connect electronics. Because ultimately, we're trying to shield electronics from transients or frequencies that are too high to be able to cause interference or even full failure of the device itself. And so we have a cable engine, which is called M-harness, which is a multi-conductor transmission line solver that has a very elaborate interface in Discovery to be able to create very complex harnesses, as you can see on the bottom right. And then even further in EMC Plus, which is not something that's part of STK Shield Plus today, is you can create more complex circuit terminations at the end of those cables to be able to handle filters and more complex diodes, for example, as you can see here. So everything is all integrated within the solver that is used in STK Shield Plus for physics and solving these problems. And so all of these are there under the hood. For Ansys Charge Plus and what we find in terms of numerical solutions in STK Shield Plus, you will see that we will be leveraging the time domain FEM solution for full wave and quasi-static electromagnetics. We'll also be using a boundary element method for electrostatics that we use for surface charging problems related to low energy plasmas that you find in space. And then we have it also coupled to the Monte Carlo particle transport code in integrated with the FEM, which allows us to model radiation hardening concerns and also dose as a function of material depth. So these are the type of capabilities that we will be able to solve with the technology of Ansys Charge Plus. Ansys Charge Plus has a lot of physics to be able to solve plasmas in space with even higher fidelity using a particle in cell. We can model electrostatic discharges using a finite difference time domain solver. And then we also have a circuit solver and for more advanced boundary conditions as well that you can tie into the electromagnetic FEM solver. So a lot of technology, but the ones we'll be focused on will be the FEM, the transport, and the BEM for STK Shield Plus. So I just want to reiterate with this slide that what we are able to do with STK Shield Plus is ensure the survivability of a mission under various radiation threats. And those radiation are coming from electromagnetic environments, from high energy particle environments, or even lower energy plasma environments that you find around the Earth. And the goal is to be able to understand how we can shield or protect the mission. It could be the aircraft, the satellite, it could be electronic devices from these environments. And so either it comes down to changing the mission parameters and change the path and the trajectory, or the actual design of the components themselves. And I understand that there can be a synergy that is built between the EMC or the rad-hard engineers and the satellite integrators, but I also know that there are ways to be able to stay below certain thresholds defined by standards by just changing the mission environment, and that's where a lot of work in STK can be done as well. So there is a synergy between the two tools. So this is what you get when you install Ansys STK Shield Plus. You have STK 13 here on this case on the left. You have a mission that is set up and put together. In this case, we have aircraft and a satellite, and I'll go into more details on this setup in a bit. And then you have the UI that gets launched for Shield Plus every time you run one of those optimized workflows. And so in this case, I present the radiation hardening options. This allows us to create a dose depth curve. And then at the bottom, you will press run, and then you will have access to the discovery interface with the settings that are needed for running the Shield Plus simulation. And the workflows are actually running and setting up the simulations automatically. So everything that you need to run one of these simulations is automatically generated through the use of our APIs by the tool itself, so that you can not have to worry about changing parameters, or you can just change them afterwards once the simulation is set up. And then the information is sent back to STK in the form of graphs and plots so that you can visualize the results in STK. So how do we launch one of these streamlined workflows? Well, this is just kind of going through this process. We have the icons at the top, and then once you launch them, you can see the STK ribbon here, 6 workflows, and I'll go into details on all of those workflows specifically, and they will match the workflows that are available in STK Shield, so you can relaunch them once you're in Shield Plus to be able to, after you've done some tweaking of the parameters, for example. So the workflows are shielding effectiveness for electromagnetics, lightning probability for calculating the risk of getting struck by lightning on a given aircraft mission, shielding effects from an overbraid from electromagnetic environments, the rad-hard workflow for being able to understand dose depth curve and model dose depth curves, surface charging for the risk of ESD on the surface between 2 different materials, and then ray tracing to understand dose at the component level on a PCB or inside a satellite. So this is an introduction to STK, very quick. We're opening a scenario that we've already built. I'm navigating to the scenario now, scenario number 4, which we generated. and we are able to, in this case, load this .sc file, which will automatically configure STK with the various objects within the scenario. For the sake of this demonstration today, we're going to have a satellite. We will configure the satellite with the seat module and the seat radiation model set up to NASA. STK13 already has IRENE. NASA is AE8, AP8. IRENE is AE9, AP9. And so we have both models there in STK. We also have an aircraft set up in this scenario just so that I can run all the modules in one go. We want the propagator for the aircraft to be set to aviator for some of our workflows to run efficiently. And then you can see, I think, at the end here that we have the mission set up with various places like Colorado, and then the satellite and the aircraft on their own respective path and trajectories. So let's dig a little deeper into the workflows themselves. So electromagnetic shielding effectiveness is a way for us to calculate a transfer function for fields through an enclosure. Our FDTD allows us to solve for this problem. You shine electromagnetic radiation onto an enclosure, and we will extract the fields inside the enclosure, and from there be able to extract shielding effectiveness. And this, as you'll see, it works well with some of the workflows in STK, and we'll show you how this works in more details in a second. Lightning risk analysis. Here we have a lot of knowledge at EMA on lightning risk, and we have shaped that into a tool to help us extract information on what the lightning risk is at various altitude of an aircraft path, or also various locations along the Earth. And so there is a lot of information that we can get in terms of understanding and defining the threat from lightning for a given mission. And so if we have a certain amplitude of current associated to lightning in a region where we know that there are very high energetic lightning, we can use those waveforms, and we can use them to do analyses like the shielding effectiveness, for example, or some of the cable shielding analysis, and make sure that we are able to shield ourselves from these risks. The cable shielding evaluation is a tool that allows us to shine electromagnetic waves onto a bench top setup with the cable defined by a certain length, and understand the coupling through the shield of the cable to the sensitive conductor on the inside. And so we automatically set up this environment and this workflow so that you can directly get the transients at the electronics at the end of the cables and make sure that those stay below a certain threshold. Then we have the radiation dose depth curve generation, which is there to be able to create a dose depth curve based on IRENE or the NASA models within STK. And then we can use those depth curves for other applications and more refined analysis. But we've also exposed other particles and the ability to create those depth curves for photons and so on that you may not have the ability to do in other tools out there. And this allows us to understand not only a dose depth curve for ionizing radiation, but also for non-ionizing radiation. From there, we can take that information and pass it to the 3D radiation dose modeling tool, which is a ray tracing solver to be able to use that dose depth curve, use the amount of material shielding between a detector point and the environment, and then extract how much dose will actually reach a certain component on a PCB, for example. And so here you can import the layout of a 3D PCB, you can import the enclosure and the whole satellite, and we will automatically run this ray tracing tool using a dose depth curve and extract the ionizing dose at any location on the PCB. And it is coupled to you can create that dose depth curve from the other workflow that we just talked about. And then last but not least is our spacecraft surface charging and ESD risk assessment tool. You can pass a geometry of a satellite, and we will automatically assign some material and the environment of interest, geo, lunar, polar, and then we will run a boundary element method to solve for the fields along the surface due to the space craft charging, the space plasma environment that we're in that you've selected from the tool, as you'll see in a second. And then you can go through the user interface of Shield Plus, change the materials or add materials in various places and see if you're still at risk for this given orbit that you've selected. So how do you launch these workflows? In STK, we have the ribbon. You can click one of these workflows once our mission is set up that I just introduced. And then you have defaults for each of the workflows and parameters to input for each of the workflows. And then we will automatically, once you run the workflow, execute and generate results for that simulation. So you don't have to do any more on the Shield Plus side unless you want to, besides what you see here, setting up the source, setting up the environment, and things that you can extract from STK basically for various missions. So the radiation hardening workflow is the one we'll start with. So this is an advanced dose depth curve generation tool. Let's say you have your mission here, in this case, GEO, and we want to start setting up some of the environments. The first thing you need to do is select the object in STK from the scenario. So our GEO sat in this case, select the shape. And by default, we're using shells. And so we generate concentric shells in Shield Plus onto which we shine radiation. Those shells are going to have a certain thickness, and this will tell us basically with the thickness of those shells, we'll have a data point as a function of thickness for the dose reaching the depth of those concentric shells. And you can shine electrons, you can shine various levels of different particles. I'll show you what those are in a second. You define the energy and the current for the flux. And then we have the exposure time. How long are you staying in this geo environment, for example? And then you define the different layers that you have in the system. You don't have to use aluminum, but you can change the layer property material if you line it up with some of the ones that are already in Shield Plus. And then here we're defining about 100 different or 110 different divisions of different thicknesses to be able to shape the waveform, the dose depth curve properly so that we can use it for the ray tracing workflow afterwards. So here are a lot of details on what each of the properties are. The shapes, we can actually do a slab or a sphere. The shell is the one we recommend because things are working more efficiently in the shell format, or else we have to actually mesh layers within each of the mesh divisions within each of the layers that we define when you use the slab or the sphere tool. The particle type, we have electrons and protons. Those are defaults from AE8 and AP8. And we have databases in STK to be able to draw the energy spectrum for these particles specifically. In case you don't use these and you want to use a photon, ion, neutron, or positron, or alpha, which are all particle types that you can select from, at that point you can select an energy and give it a monoenergetic value and understand and create a dose depth curve for those as well. We have to define the current and the flux of particles on the target that will actually define the total amount of radiation as a function of thickness. So those dose depth curve are generated for a given environment and a given exposure. So we have to account for that. Very easy to regenerate if you change the exposure time. You have to define the thickness of the target on the inside of all the shells. And then we have to define the exposure time and the different types of materials. The material library from Shield Plus is exposed here in the selected material tool. So every time you create an add layer, it will create a layer of that material. So that if you need additional ones, we can add those in Shield Plus as well. So what does it do ultimately? It will create an open Shield Plus with shells, and it will actually run the full radiation transport code with all the physics that is present and associated to that. And we will then extract at each of those data points that we generated, all the layers, the dose and rad, which is a dose depth curve that we can then use for additional analyses. Here we are showing validation against standard. So we regenerated the dose depth curves for electrons in a geo environment that is provided by the cross-program design specification document. And we can show you here very well that we're able to reproduce that effect as a function of depth. And so if you are now trying a different environment that is not in a standard, maybe you don't want to design to worst case geo, but you actually want to design to a more specific tailored ephemeris for your mission, then you can generate the dose depth curve for that and design and then do your radiation hardening specifically for this profile. And so here is an example of LEO proton on the right as well. And we're able to compare the full Monte Carlo analysis that we did compared to the standard. So what do you do with the dose depth curve? The next step is to actually start running ionizing dose simulations. And so this is where the ray tracing workflow comes in. You can provide the dose depth curve that we just generated, provide a geometry of your enclosure, PCB or satellites, and then we will automatically create detectors at each of the locations of the geometry that you're passing. And you can also add additional thickness if you want as well to be able to define, if you don't want to model the satellite, but you want to estimate it as an inch of aluminum, you can actually just add extra thickness to see what the true radiation will be once it reaches the components inside the satellite. Rays per origin, this is how we do ray tracing. We are shooting at each mesh node a set of rays that will be interacting with the CAD geometry, so we can calculate the total amount of thickness and then extract from the dose depth curve the actual ionizing dose on the system. This is run on GPU. This workflow specifically, we're using NVIDIA optics libraries, which are very efficient at doing ray tracing. So we can run a lot of rays for these problems and do very high fidelity problems to extract dose on the system. And I'll show you what that looks like on an example model. Here are some details on what the parameters are. The dose depth curve is a very simple file with a thickness and dose and rad as a function on the right that you can see here. So in case you also have a dose depth curve that you've already been provided, you don't have to regenerate it. You just need to have it in this simple format on the right here without any headers and use it as an input to the tool, and you will be able to start doing ray tracing. So the example problem we'll use here is an electronics box that was not designed for space. It has actually very minimal shielding. There's a radiator at the top, and there is a lot of holes for connectors onto the outside environment. And you'll be able to see even that there are some gaps in the walls as well. The point here is to showcase what happens if you were to send something that was not designed for space in space, but also just understand the complexity of the problems that we can solve here. A lot of different components on the board. The way design is done is by sometimes moving around things or moving the PCBs or adding additional shielding in various places. Here, it's very easy in our tool to run these problems. There is minimal if no needed for CAD simplification, and you'll be able to get started with the ray tracing. One thing that we are trying to do is at first, the tool will automatically assign aluminum to everything, and then you can go back through Shield Plus and the discovery interface and change the properties if you want to get more information. Ultimately, we'll extract something that you see on the bottom right here, which is the ionizing dose on each of the components that you of interest in the system. And then you can also look at rays for some of these analyses to understand the location of where the holes are present. Those rays will be the out of those 2,000 or 20,000 rays that we're shooting at each location where we're probing information, we're going to be extracting the 1,000 least shielded rays. And so in this case, we're able to see that we're pointing at the holes that we were just highlighting in the geometry. And so here are the results that we would get in the setup. We are getting ionizing estimated dose from the dose depth curve at each of the components of interest. And so here we're able to see that some of the components that are close, here we have a surface near a connector on the top here where there's a lot of gaps, and we're able to see that we have very high level of radiation compared to some of the components that are on the inside for the dose depth curve that was chosen and generated in this setup. So this is very powerful to be able to do these analyses and make sure that you stay below a certain threshold for a change in environment. Next one is the satellite surface charging for electrostatic discharge risk assessments. So in this case, we are flying, for example, in LEO or in GEO. You may be going all the way to the moon. So what we have provided is the ability to define an environment. The solution that we're using to model these various environments often by standards has to change based on the energy of the plasma. In our case here for this tool and for the quick assessment, we have defined an analytic version for the energy and the density of the plasmas in each of these regions. So this is not tied to AE8 or AE9 because AE8 and AE9 really look at the high energy component of the plasmas that are out in space. When we're doing surface charging problems, we have to worry about lower energy components, and we don't actually have databases that give us that low energy distribution at this time. So we use standards to be able to define the worst case scenario for these various environments. So the environments that we have defined in here for the quick assessments are GEO, Aurora, LEO, Lunar, and Polar. And we have some settings that are present to make sure that to make sure that you can at least get a sensical result in terms of the charging across various surfaces on the satellite. We do recommend going and doing further analysis if we feel like there is a charging concern, but this is a quick way to make sure that if you change your orbit or if you're trying to go to GEO to test to see if your LEO satellite is viable in GEO, for example. Okay, so here's a quick demo. So we're loading a scenario. In this case, we're going to have a location and a satellite that we're going to be setting up. And then we want to start running the surface charging workflow. So we have to give it the geometry. Then we define the geo environment in this case, and then we just press run. And then you'll have the pop-up for STK Shield Plus that shows up. And then as the tool opens discovery, it will load the geometry inside the tool, which is in this case, the human space capsule. And then we will automatically assign the environment for geo. Surface material, everything will be assigned to aluminum to get started. And then we will also mesh the geometry and run the solution through our boundary element method. You can see here we're using a 1.5 meter mesh, so it's pretty coarse, but the mesh engine automatically refines the mesh and some of the features. And then we start time stepping through the process until we converge to a solution. In this case, it takes about 100 seconds to reach equilibrium in terms of the charging. So what we did is we literally just placed the satellite and dumped it in a geoplasma environment. And so there's going to be, we're at first at 0 volt on the surface with respect to the plasma, and then we converge to a certain result in the tool. And then we actually upload those results. You can visualize them in Shield Plus, but you can also see them directly in STK as well. Let me see if I have it here. So then you go to STK, and then you can see the potential that we just calculated. And so you can make a sense. Usually the assessment for these simulation is looking at potential between one surface and the other. In this case, everything is in aluminum, and so everything is charging to the same level. But if you have different materials at the surface, then you wouldn't get that same result. You may have a different potential for one material and one surface and another. And that differential voltage is what we want to minimize to make sure that we don't actually get a risk of discharge. And so we are shielding ourselves in some way from the space environment by making sure that we choose proper materials at the surface or proper spacing between surfaces that have materials that are dielectric or conductive. The next workflow I want to tackle is the electromagnetic shielding effectiveness workflow. So we're running a full wave electromagnetic simulation to make sure that we have an electromagnetic compatible enclosure based on some various environments that you may be exposed to. So this is we'll use the aircraft in our scenario. In this case, we have to select the objects, select the geometry of the enclosure as well. We have to define a simple setting for the mesh, but this is the default and it works just fine. And then we have to define the source. So the Gaussian electromagnetic pulse that is going to be applied to this enclosure, so that we can assess how much penetrates through the enclosure, what the transfer function is, and then we can actually scale that transfer function to any threat that you may have calculated in a tool in STK, maybe from the RF antenna modules that are present. So a little more details on the tools that are needed. You have to select an object as well. This is key because it just allows us to pass the results back to STK. And then the Gaussian source here, we have the amplitude of the source, we have the width, and also the time to peak. And then the direction is important because you're importing a CAD, and then we're going to be shining that pulse from a certain direction, and it will penetrate on one side of the geometry, and it will not be the same result if you apply it onto another side in terms of what the transfer function is. And so we want to account for this, the orientation of the signal, where it's coming from, and the orientation of the CAD are all critical in solving these problems. So here is an example. You can click the shielding effectiveness tool in the ribbon, start loading some of these options that we talked about. Here we're navigating to an enclosure that is part of our tutorials. It's the just simple shielding effectiveness blank workflow. And then we have some of these settings here. We'll be setting this to 50 so that we set the proper time spatial grid for the full wave solver. And then the direction on which we're going to shine the electromagnetic wave. So we run the tool, it opens the CAD, this enclosure that we have here. We're shining from the minus Y direction, and then very quickly we run the simulation. We've set up the Gaussian source. We've actually set up a field probe on the inside, and we've assigned everything to metal on the enclosure. Material properties will matter, and so if we have to change that, we can. And then we run the tool, get the results, execute on the FFT that needs to happen for us to get the proper shielding effectiveness as a function of frequency. And then we report on that back in STK. And so this will tell us which frequency we are sensitive to for this Gaussian that we've applied. And then we can also get the transfer function that we just calculated as part of shielding effectiveness, and we can change and scale that by any RF sources that you may have obtained from an antenna or a source in your mission. And so depending on the orientation and how long you're exposed to that source, we can calculate and assess if we are reaching a certain threshold that is problematic for the system. There's a lot of various things that we look at because we are solving at fields in 3D inside the whole system. And so when we run these tools, you can look at field statistics that made it on the inside. So here we're looking at electric field and processing all the electric fields from our probes. So we have the shielding effectiveness and also the electric fields at various frequencies inside the system. We always want to keep those below a certain level, or else we're going to have a problem in terms of the susceptibility of the equipment within the enclosure. So shielding ourselves from these electromagnetic environments, that they are from lightning, from systems, EMPs, or even from just natural electromagnetic sources, we want to make sure that we can sustain and have the proper shielding at the CAD level or at the structural level. So I think one thing that we want to understand is how do we tie this into STK? And one thing I wanted to emphasize is that STK has some RF analysis tools that we can leverage. You can leverage the results from gain and various results that you get from this tool. And then you can scale the shielding effectiveness values that we get to be able to get the total amount of fields that are going to make it inside the enclosure due to the radiation that was generated from your other analysis. And this will tell us if you're exceeding a certain threshold, and we can make some design changes or some mission path changes based on that information. The next thing that we want to be able to shield are susceptible conductors in a cable harness. And so we have created a workflow to automatically, instead of looking at shielding effectiveness of an enclosure, we're looking at shielding effectiveness of a cable. We can provide the cable length the termination resistance to understand the transients that are going to make it to the end of the cable and where the electronics are, to assess the susceptibility of the electronics to the coupling of radiation onto the cable. And then we have the same electromagnetic pulse that we're applying to the system, so the Gaussian waveform. So one thing that we can vary as an input today is the length of the cable. Depending on how long the cable is, you're going to have various susceptibility. You can change the termination as well in terms of the resistance, because that will also change the transients that are making it to the components. And there is a shield that is defined in here. I'll show you how that is set up in a little bit. So we click the over workflow here. We set up the various parameters. Select a direction. This is important because our workflow automatically creates the test bench that we're looking at with a ground plane and then electronic boxes on the top. And that is going to be on the minus Z direction, the ground plane. So if you shine a source from the minus Z direction, there's not going to be any coupling because of the ground plane that is present. So always select one of those good selections. And then the tool pops up. Automatically, we create the geometry. So these are the electronic boxes. And then we have the cables, and we assign the harness properties onto the tool. So this is how we're using the transmission line model. We're not actually solving this in full wave to make these simulations much quicker. And we're shining this electromagnetic wave onto this Gaussian pulse onto the system to get the transients that are induced through the shielded conductor that we've applied on here. So we're actually probing a lot of information on this setup. We're probing the voltage probe, the voltages from the shield, the current on the shields, and we're reporting on all this information in STK. So you can see from the name of the plots what we're looking at, and in this case we're looking at the voltage onto the shield. And so we're reaching some transients that we have to be able to mitigate based on the environment that we're exposed to. So this is what the cable looks like. We'll show you how to change that, but for now it's just a shielded conductor. And this is what a Gaussian waveform looks like with the settings that we've applied onto the system. The same one as for the shielding effectiveness. It has a frequency content. It is about a nanosecond pulse width. It has a response onto the system that can be very drastic. And so these are the type of effects that we want to mitigate. And so how do you alter the response on this cable? There's various things we can change. We can change the load at each of the terminations of the cable. We can change the length of the cable, the direction of the propagation, the properties of the Gaussian pulse. And these are things that we can obtain from an RF simulation or scenario that was designed in STK. And then if you want to change the cable properties, you can actually do that in Shield Plus directly. You can go to edit the shield, and you can change some of the from our library, for example, if you want to change the conductor itself, if you want to change the jacket properties, some of the transfer inductance properties of the shield as well can be changed here depending on what you want to have under test. And then this will be what is used in your tool when you rerun the simulation and get the proper shielding effectiveness based on that. So the proper conductor transients that are generated based on the changes that you make here. So last is our lightning risk analysis for STK Shield Plus. So here we want to be able to understand based on an aircraft mission what the lightning strike risk is and the mission failure risk is. And so we have tools that we have exposed and information that we can provide based on the scenario that is designed. So we're selecting our aircraft. It has an actual trajectory in STK, and then we give it the script that we want to run. So we have various analyses that we can run. In this case, we're going to do a risk to amplitude analysis. And then you define the amplitude of the waveform. And then we have also the ConOps factor that have to be provided. So there's a couple details here. We do require the aircraft to use the aviator mode so that we can extract the path properly using that module from STK. Then there are two different scripts, the risk to amplitude and the risk input. These are two different things and then the amplitude to risk. So we have various ways to run this analysis and get you the information that you need. And And then here we can go ahead and run the solution. So we go through the process. We can run the aviator selection, select the script that we want to run, provide the ConOps factor, and then we provide a lot of information about the lightning risk as a function of altitude. And so we send all that information back to STK so that you have access to it. You can see the different lightning waveforms, for example, that we can use for further analyses. You can see the risk of lightning strike, the peak current that is associated to a given lightning location. All of this is very useful when we want to do, for example, the next step, which is understand how to shield ourselves from these environments and these natural effects that are present on a given trajectory. So that's the first introduction to all these workflows. I was very excited to be able to show you those capabilities. I'm sure we have some questions on how to leverage these tools. I think we're here to help. If you have any questions, you can always reach out to Ansys and to us, and if we're not able to answer them today.
Excellent. Thank you very much for such an informative presentation, Kevin. We can now transition into the Q&A portion of the webinar. As a reminder, attendees are encouraged to submit questions to the team's Q&A feature during this time. So with that, let's begin reviewing the questions we've received. The first one is, can the lightning probability capability be used for ground or maritime applications, or is it only limited to aircraft?
I think the answer is yes. Yep, we can extract that information near ground. Yep.
Okay. Next question is, does using these capabilities require the STK user to also have EMC Plus and or Charge Plus installed on the same machine, or is everything integrated within STK? Does using these capabilities within STK use the associated licenses, or are they included in the STK license?
Great question. So Ansys STK Shield Plus is a module to STK. It has all the capabilities that you would need to run these workflows, but it runs on its own license. It's an STK Shield Plus increment. Yep. So it's a different product in that way than STK Enterprise.
Great. Next question, do you have to have NVIDIA GPUs for the ray tracing workflow? Is that
Yes.
a hard requirement, or will it default to traditional CPU based in absence of supported GPU?
Yeah, today is a hard requirement for that workflow.
What model formats can be used or imported in this package?
We typically use the discovery format. So you can open the discovery interface and set up the problem in the CAD geometry. And then we will use that. The discovery interface can load any step file, any CATIA file and object files that you may have from your other CAD tools. And then STK Shield Plus will load in that Disco file.
Okay, next question is there any sort of parametric and or optimization type of capabilities for any of the workflows that we saw today?
There are, but not in STK Shield Plus. For those, I would recommend going with EMC Plus and Charge Plus if you need to elevate the level of parameterization and analyses that you want to do at this time.
Okay. When using the seat module, what do you put in the energy column?
I would have to double check. Maybe we can take this one offline and respond by email.
Sounds good. Is the enclosure placed in aircraft for shielding effectiveness workflows?
It's not. It's placed. It's not placed within the aircraft. If you wanted to have an aircraft around it, you would have to place it before and have the aircraft present, and then do the shielding effectiveness workflow. So you have to place it manually.
And then we have another follow-up question. Are there example workflows available in the tool?
Yeah, so all the workflows that I presented today, we are going to um, explicitly have them available for people to reproduce as part of the tool as tutorials.
Okay, and next question is is the Gaussian waveform generated? I'm sorry, I'm not sure I understand this question. Is Gaussian waveform generates from SDK environment?
No, so the Gaussian waveform is the input that we use for our Shield Plus simulation. You can tweak it to match an environment from STK, or you can use the results that we get from the Gaussian waveform that we apply, and it can be used to extract a transfer function onto the components inside the enclosure or on the cable to then scale it with respect to the amplitude of the radiation that you may get from your RF solution in STK. So it's used to be able to understand the thread, but if you are worried about the frequency content, at that point we would just scale the frequency response that we get from the shielding effectiveness analysis to the threat environment that you simulated in the other module in STK.
Okay. And the next question is, does this plugin leverage existing models from STK's seat? Will it respect the model the user has configured in STK, for example, Irene, NASA, etc.?
Yeah, so the dose depth curve generation tool will leverage the STK seat module choice that was chosen, like the NASA or Irene.
Okay. Next question is, where is a cable placed in a place object? I'm sorry, I'm not sure I quite understand that question. If that
Yeah, so we have, I'll try to say something to it. The cable shielding workflow automatically places the cable as you saw from the workflow. You can go back and change that setting once you have Shield Plus open and the Discovery interface open if you want to move things around. If you want to understand cables for shielding effectiveness, for example, those you can place those cables in the CAD before you launch the workflow and assess the susceptibility of those cables then, for example. So that would be one option, but you would have to do it manually in the CAD before launching the workflow.
okay? And currently, our last question is, generally, what inputs does STK give to Shield Plus?
Yeah, so for the um, for the lightning probability, we use the aircraft trajectory. For the dose depth curve generator, we use NASA and seats, the NASA module and the Irene module and seat. For the other ones, we have to manually kind of scale the amplitudes or the results based on the results obtained from another module. But the only those two workflows today are directly leveraging these inputs from STK.
Okay, great. Seeing no other questions, I believe it's time to conclude this session. Following today's webinar, all registrants will receive an email from EMA with a link to the recording of this presentation. If you have any questions about a particular section of interest to you, please feel free to respond directly to that email or through the ema3d.com website. Next up in the EMA Solving Electromagnetic Challenges webinar series is Ansys EMC Plus and Ansys Charge Plus, What's New in 2025 R2, which will occur on August 20th at 11 a.m. Mountain, 1 p.m. Eastern. Thank you all very much for your time and attention, and have a great rest of your day.